Welcome everyone to a very special Q&A. My name is Sanskriti Deva. I'm a product marketing manager here at IBM Quantum, and today I'm joined with not one, not two, but three amazing experts. We have Andre He, who's a quantum hardware developer, Majo Lozano, who's a quantum hardware engineer, and Ali Javadi, who's a principal research scientist. Today they went over quantum benchmarking and low overhead error detection with space-time codes, and they're very excited to be joining us today. Do you guys have any starting words before we dive into these questions?
Um, Thank you so much for having us on Scrutiny. I'll be happy to answer all the questions you guys have about benchmarking at least.
Oh, Ali, I think you might be muted.
Yes, sorry, I was muted. I just want to say hi to everybody and thank you for taking the time to watch the lectures and happy to answer any questions. And thanks to you guys for facilitating.
Awesome. Andre, any starting words? Oh, I think we might have lost Andre really quickly. Well, with that, let's go ahead and dive into the questions. So, the first question is from Handy. With QED protocol, you said that there's no error correction. Then, how does the fidelity improve while adding more gates? And then there's a second part to this question, which I can mention after we answer this first part.
Sure. So this is about quantum error detection. Um, right. So in quantum error detection, in contrast with quantum error correction, I mean, both of them, you're basically adding some extra qubits and some extra gates, whose job is basically to detect the that some errors happen. In error detection, what we do is kind of simple. We just, once we detect an error happens, we discard the run, right? In quantum error correction, we attempt to also correct it. So in error correction, there is no discarded run, right? Like we attempt to fix everything. Sometimes we fail, but we never just discard something. In error detection, right? Like imagine you have a circuit and you're interested in some output. You run the circuit 1,000 times. This is typically what you do anyway, right? In order to, because in quantum you don't just run once, right? Typically you're interested in some population, maybe some average value. Um, so anyway, you run 1,000 times. Out of those 1,000 runs, maybe 200 of them triggered an error, like in these flag gadgets that you add around your payload. So those 200 just get discarded. We don't even look at them. Of the remaining 800, we just say, okay, these are the ones that I did not detect an error in. So let me compute whatever value I was interested in, some expectation value or some probability, whatever it is. Uh, on those remaining 800. And then just by virtue of those 800 not having triggered any error, any flags or any errors, those are higher quality. So the fidelity goes up. But notice that the price that we paid was the discarding. So we discarded some of the runs. Um, so yeah, so that's generally how it works. If there are any, I don't know if that answered the question or if there are any follow-on questions about that.
Yeah, so you touched on this briefly, but the follow-up question is, does the fidelity calculation, is it based on undetected error states? And if yes, how do you compare the one side and space-time protocol? Like, do you prepare it to reach the same number of accepted states or shots?
Um, right. So like okay, so I guess maybe the question is about the confidence that we have, right? So say you're interested in computing some expectation value um, of some quantity, some observable from a quantum circuit, right? Um, Typically, what you do, say your quantum computer is even noiseless, right? So there's no noise. I just what you have to do is you have to run the same circuit multiple times, measure a bunch of outputs and then compute the expectation value from that. Okay, and the more runs you have, so like kind of your confidence in the value that you're estimating grows with the number of shots that you do. Okay, so typically as like the 1/square root of the number of shots. So if you see these plots, you see this confidence appears an error bar. So you have some value with an error bar around it. And then you take more and more shots and this error bar shrinks. Okay. So now with this error detection protocol, what we do is we just take our shot out of these shots that we're taking, some of them get discarded, right? So the ones that we keep come in at a slower rate, right? So suppose you can take one shot every, I don't know, every millisecond. Um, so you take 1,000 shots, it takes a second. Um, but if you have a discard rate of 50%, then it takes 2 seconds for 1,000 good shots to come in, right? So it takes longer. So the computer is kind of slowed down, but ultimately the number of shots that you require for the error bar to shrink to the accepted level finally comes in at some point. It just comes in slower. And that's it, right? So you have to, the price is basically a slowdown of the quantum computer because of the discarding that happens. But you just continue taking the required amount of shots to reach that accuracy or the confidence that you need.
That makes a lot of sense. Thank you. And then our next question is also about error characterization. What are the error characterization experiments for n qubits effect on each other and for n gates effect on each other? So they gave an example. If I performed an experiment like T1 or Han or RB, but for multiple neighboring qubits simultaneously, is this sufficient to study the effect of the qubits on each other? And I'll throw this out to anyone who would like to take it.
Yeah, I think I can maybe give a answer to this. Yeah, so for all of these characterization experiments that we do, necessarily, like qubits will talk to each other. So T1s, T2s, gate errors that you may measure with different sets of neighboring qubits may be different, especially if there's a high level of crosstalk between these qubits. Uh, and that's dependent on your device layout, the types of gates that we're using. For example, like CR, the CR gates that we use in our Eagles versus the CZ gates that we use with our Herons, which have tunable couplers. Which and this architecture greatly reduces the amount of crosstalk that we see when we're running these gates. So long story short, for a lot of these figures, the exact number that you will pull out for these benchmarks will differ depending on the topology of the circuit that you're running and the number of neighbors that you're running for each qubit. Which is why it's important that when you're looking at these benchmarks, especially if you're measuring these benchmarks yourself, trying to use these to map to say like map a circuit to a certain set of qubits that I guess you're aware of how that affects. Like ideally, you'd want to benchmark your qubits under the same conditions that you might be running your circuit of interest with.
Got it. No, it's
I think
very
one,
well explained.
yeah.
Go ahead,
If I
Maho.
may add to that, maybe from like a benchmarking point of view, if what people are interested in is in characterizing the crosstalk or like the interactions in between qubits, I think I would suggest definitely running some sort of like simultaneous like randomized benchmarking experiment. Um, and if you can recall the lecture that I was part of, I briefly talked about a benchmark that we do here that we call layer fidelity. And it's basically just a way of running like simultaneous, like randomized benchmarking on, a qubit chain. And one really nice advantage of running this benchmark, say over like isolated RB is that you are able to, to capture these like interaction terms that you otherwise wouldn't.
Got it. No, that makes a lot of sense, and I think that answers the question perfectly. So, our next question, when building the BFS breadth first search tree for GHZ state creation, do you also take into account the connectivity between the qubits for optimal control of logical operations in the future? And this is assuming that the GHZ state creation is done with the idea of creating a logical qubit.
Um, I'm not sure I understand the question. So maybe I'll just say my interpretation, and then you can, if I'm wrong, just ask again. But okay, so in the GHD state preparation that I showed, um, right. So this BFS search is used to right. So what is the goal in GHD? We're interested in entangling um, a bunch of qubits in the shortest depth possible, right? Um, and breadth first search is a way of doing this where we start from some qubit that kind of lies in the middle of your chip, and then you kind of explore layer by layer your surroundings, your neighborhood, until you kind of reach the number of qubits that you want. So this is just the basic breadth first search. Um, and yes, so the connectivity is considered here, right? Because the neighbors are the qubits that can talk to each other. So like you start from the middle, and then maybe that middle qubit has three neighbors. So you entangle those three, and then now you have like three leaves. Each of those maybe have like a bunch of neighbors. So then you go and so you are walking along this connectivity graph. Um, and then I did not quite understand the relation to logical qubits. So okay, so again, like it's the terminology is gets kind of mixed up sometimes. So when we say logical qubit, typically people think of error correction, but you could also like here logical qubits are kind of just a way of distinguishing between those qubits that are in your GHZ and then those qubits that are not part of your GHZ but are still part of the circuit, and they are just acting as flags for the purpose of error detection. So if you want to call that, logical versus non-logical, then that's fine. And so yeah, so then like if I make a 100 qubit GHZ state, right, and then I use like 10 extra qubits. So like in my experiment in my circuit, there are 110 qubits working. 100 of them are carrying this GHZ state, and then 10 of them are just kind of entangling into that. They are not really doing anything from like the computation point of view, but what they are doing is if an error happens, it kind of triggers them or they detect it. So yeah, so that's kind of
Yeah, that was my interpretation of the question as well. But feel free to ask follow-up questions if that didn't answer it. But yeah, awesome. So we'll go ahead and move on to the next question. Why is it that in the calibration sheets, some values remain unchanged for more than a day and other values change more frequently? Is there a rule for updating the errors that IBM follow? All right, any takers?
Yeah, I can take a stab at this one. I'm assuming that you're talking about the device map that's displayed on these on I guess on the IBM Quantum service. Yeah, some values may remain unchanged for more than a day versus other ones because just due to the way that we schedule our calibrations, we might not necessarily measure all of the qubits in the same experiment, and some of the and some benchmarks for some reasons will be measured on different times on different sets of qubits. So long story short, some of these get just updated in an asynchronous way by design of our calibration schedule that we run on the back ends.
Got it. Anything else to add from anyone? Great. Let's go ahead. Oh, wow, did you raise your hand? Okay, cool. Great. Let's go ahead and go to the next question. These questions are amazing, by the way, so please keep them coming. Our next question is about the Hahn experiment versus the Ramsey experiment. Essentially, this person is asking, why is the Hahn experiment used for T2 and not the Ramsey experiment? I believe they're referring to the Hahn echo experiment to measure T2 instead of just the Ramsey experiment, since um, the Ramsey experiment is for filtering some frequencies. Why would you want to filter those frequencies if they contribute to error? Awesome. Any takers?
Yeah, I can, I guess, also take a stab at this one. Yeah, so I guess the T2 Han experiment that we use, we do these echo sequences at the, I guess, at the beginning of the and end of the circuit to I guess filter out noise. And basically, as one adds more echoes to this sequence, the I guess shape of the shape, basically the shape of the filter changes, grows more narrow in terms of frequency. And yeah, I guess yeah, there is a bit of subtlety in terms of like what kind of I guess like how many echoes do we use, and what type of experiments that we runs. I guess like what type of experiment does one care about, that's reported. And I think that at the end of the day, that honestly really kind of depends on like what one uh I guess like what application one is interested in.
Got it. That makes a lot of sense. I'll do a little pun and say you really echoed that point home. Our next question is when removing bad nodes from a graph, like in the example of preparing the GHZ states, which noises are taken into account? Is it only T1 and T2 times, or also crosstalk parameters slash other parameters that influence gate execution?
Okay, so I guess I can talk about the experiment that I did, but it's not an exact science. It's kind of a heuristic, right? So you could do all of it, all of the above that you mentioned. In my experiment, I basically, um, I kind of just removed those nodes or edges that were seemed really bad or kind of broken, maybe. And the reason is I was interested in preparing very large GHD states, right, like 100 or 120 qubits. So in a 150 qubit chip, there's not much room to remove much, right? Like if you start removing a lot, then you end up with either not enough qubits or qubits that are very sparsely connected, so that it's hard to just make the GC state in a short depth. So I was being more forgiving to bad error rates, hoping that the error detection mechanism catches a lot of the errors. Um, but yeah, like so for example, I think the biggest experiment there were 120 GHD qubits plus if I remember correctly, 10 or 15 detectors, like error detectors. So that, add them up and that's taking up most of the chip. So we don't want to remove too much. But if you have, a smaller experiment, then you could take into account a lot of those, right? Like if there's a bad readout or the bad T2 or something like that, and then yeah, you could remove them. And the nice thing is that all of these are reported from the backend to Qiskit. So you could just, you can easily write a script to filter bad nodes or bad edges.
Yeah.
Wow.
Thank you for yeah, thank you for your response, Ali. I think everything you say makes a lot of sense. And if I may add one point to it, I think it's I would like to start by saying that this is a really good question. It's like an active area of research or of interest. One thing that we could also add to determine which nodes to remove would be like just error characterization methods like RB or layer fidelity. Um, besides just doing like T1, T2, or readout. And sometimes I would even argue that depending on the type of circuit or the type of problem that you're interested in solving, I would even argue that layer fidelity or, like randomized benchmarking might be more important to run than T1 or T2 because like those metrics like randomized benchmarking are basically in a way they're like a proxy for all these other metrics, so like they will already like encapsulate them. So if you have if you have a bad like error, it could be maybe because there's like already like crosstalk going on. So I think it depends, but you should also be careful about how many nodes you want to remove, as Ali was saying, because depending on how big of a circuit you want to run, if you end up removing too many nodes from your graph, then the amount of possible layouts that yeah, you end up getting is much smaller. And like sometimes you may not even get like a possible layout. So like just make sure that you are removing the one that really need to be removed and Just,
Yeah, thanks
Wow.
for that. Actually, maybe I will just add one last comment about this. So this is, I guess, if so, what I did was I just looked at the metrics that are reported by the backend, and this is fine. I mean, yeah, it works well. But if you're really interested in like the ultimate performance, one thing I would suggest is that you could also characterize these things yourself because there might be some drift in time. There could be like transient errors and TLSs and things like this that don't really pop up in the reported data. That could be from a few hours ago. But there are, I think there are repositories on like Qiskit device benchmarking and things like this that you can just run these experiments yourself. Like you can characterize T1 of all of the qubits, the two qubit error rate of all the qubits. You could do that, or layer fidelity, and to like really build confidence in the qubits that you do select for your experiment.
That is great. We have all those benchmarks or experiments on the Qiskit device benchmarking repo. And also, if you're interested in more of a style type of learning, we have like a real-time characterization tutorial in our IVMQ like learning platform. So
Oh,
that'll show you how to run all these characterization experiments prior to running the circuit that you're interested in. And we
wow.
update our tutorials in a frequent basis. So always trying to make sure to stay up to date with the most, important ones.
That's awesome. So, no, I love that answer because it kind of shows all of the resources and tools that are now available to developers for the different layers of abstractions that they want with their results. So, very exciting. It's crazy how we've gone from like 1 qubit to you said over like 120 plus with all of these experiments. And so, with our next question, if we zoom out a little bit and look at noise overall, how do factors like temperature fluctuations or electromagnetic interference or leakage errors in the quantum hardware environment contribute to specific types of noise, e.g., like dephasing, amplitude damping, and how is that characterized in the benchmarks? Let that sink in for a moment. Any takers?
Yes.
Andre or
Sorry,
Majo?
I'm trying to answer a question in the chat right now by pulling a link. So
Yeah.
Sure. I
Maybe
can
I
answer
can.
that.
Oh.
Oh,
Uh.
you go ahead. I can answer the one in the chat real quick.
Okay. Yeah, I think maybe I can speak about this a little bit. Yeah, so one of the things is that for these superconducting qubit architectures that we use here at IBM, we have to cool them down to very low temperatures in dilution for refrigerators. Um, uh, in order to operate them. So yes, definitely there is a happy window that we operate our that we operate our devices in. So certainly things like if there's a fault in in the dilution fridge, and we have say like a catastrophic warm up or something like that that will certainly affect the qubits and as I guess as quantum hardware engineers, we have monitoring experiments that kind of continuously monitor these things on our computers so that we make sure that I guess these other environmental factors affect our qubits as little as possible. So things like the temperature in the like the mixing chamber of the dill fridge itself, temperature of say even like the control electronics for all of our computers and stuff like for all of our devices and stuff like that. So yeah, certainly these like the I guess environmental factors surrounding the qubit, surrounding all of the hardware that we use to control our qubits, all say can affect the noise that our devices experience and also kind of like the signal integrity of the the pulses that we generate. I yeah, and I think that's maybe where I'll end.
No, awesome. That's really interesting to hear. And I feel like that is a good segue into our next question, unless someone has anything to add. Cool. So, zooming out a little bit more, um, we have a question on architectures. Are we comparing the IBM quantum computers only or other architectures produced in the university research centers?
Um, I guess for this question, um, I guess I'm not exactly sure. I guess comparing to what like for for certain different architectures, I guess may have some features that are more amenable to certain types of benchmarks. Say for example, cube quantum computer architectures that have very very high degrees of connectivity for say example like trapped ion or like neutral atom systems. They've very very high quantum volumes have been demonstrated with those types of devices. So certainly between different architectures, there are nuances between how certain benchmarks might favor certain properties of certain architectures. And it's also really important, I think, to understand kind of like the context in which these benchmarks are taken, because certain types of devices might run certain types of algorithms better than others.
Yeah. And then again, benchmarking is like a constant area of research. And as our devices and other people's devices, get developed or improve, we also need to update our benchmarks so that they can reflect, which type of limitations they might have or, capabilities. So I think like for example, a couple years ago we started with quantum volume and now we have transitioned to like layer fidelity. So I think it's important for us to like recognize all the metrics that we have, like measure them, but also like be aware of like what the advantages of each benchmarks are.
Got it. So we have about six-ish minutes left. So I think we have time for two more questions. Um, the top rated one right now is how can one compute or estimate depolarizing error probabilities for a specific hardware platform for both 1 and 2 qubit gates if they're not directly provided in the calibration data? And then there's a second question which says, could a global average from randomized benchmarking data be used to estimate these error probabilities? We'll let you
Wait,
guys take that in. Go ahead.
sorry, for the second, can you repeat the second question?
Yes. Could a global average from randomized benchmarking data be used to estimate these probabilities?
Like error probabilities, you mean?
Yes.
I'm not entirely sure what it is meant by global, but if by global it's meant to say take all the qubit averages and then condense them into one number and then use that as the error probability, I would not necessarily advise um doing that because like no quantum computers like all the qubits they have their own properties. And it's really important when dealing with this type of hardware to like know which like regions in the device to use for like specific experiments. And not all the regions will perform the same way. So qubit 0, for example, might have a really small error, but then qubit 100 might have a larger error. And if you took the average, you would get, an error in the middle. But that wouldn't really tell you where on the device map you want to map your circuit into. So because these type of circuits or experiments are highly dependable on the region that you select, I think it's really important for you to take that distinction. So I would not advise using a global number that somehow encapsulates the entire, like average randomized benchmarking error.
Got it. And that leads into our next question, which will be our last question, I believe, based on the time we have. Is this error correction slash error mitigation technique vary according to qubit types? And I think they're talking about all of the techniques that were discussed today.
Um, whether the techniques vary according to type of qubits. Okay, so one thing that makes a large impact on error detection slash correction is connectivity of qubits. Because what happens in error detection or correction, right? Like what you're doing is you're measuring syndromes, and these syndromes are what tell you that something went wrong. Um, and then to measure syndromes, you have to kind of probe into your payload, your logical qubit, and measure something about them, right? So, like, first of all, why don't we just measure the data qubits directly? Well, because doing that, in a classical program, this is actually what you do. Like you do assertion, for example, in a classical program, you like kind of look at the data to make sure it's staying. It passes some sanity checks, it's correct. You can't do that in quantum because measuring the data just collapses it, and you kind of destroy the information. So what instead we use these ancilla qubits. We use them to probe into the data, into the payload, without learning anything about the state of it, but only learning something about the errors that happen. So it's a very subtle thing, right? But then the connectivity, like, it makes a large impact because if you can just probe anywhere at any time you want, you can do a lot, right? Part of what I presented in my lecture was kind of trying to deal with the reality in superconducting qubits that you know, usually you have planar connectivity, you have limited connectivity, every qubit can interact with its neighbors. So kind of that kind of ties your hands quite a bit. Um, so for example, in neutral atoms or ion traps, people can try, a lot of different codes that are not necessarily concerned with connectivity of qubits, and they kind of assume all-to-all connectivity. Um, the superconducting qubits, this matters a lot. Um, Other than that, I guess one other thing I would say is error detection, as I said, relies on discarding erroneous shots, right? And so, depending on the amount of noise in the system, you might end up discarding a lot, right? So if you're dealing with a very large, very noisy circuit, and you're putting these probes or detectors around it and detecting errors, they trigger a lot of time, like maybe even 90% or 99% of the time, because there's just a lot of noise in the circuit. And so, in those settings, it helps a lot for your qubits to be fast, your gates to be fast. And that's a big advantage of superconducting devices versus ion traps or neutral atoms, right? Like in superconducting devices, we can take a sample or a shot in like a millisecond or something like around. Sorry, microsecond dish. And so in neutral atoms or ion traps, this is about 1,000 times slower, maybe even more. And so doing error detection there is going to be kind of painful, right? Like if you're going to discard a lot of shots and only retain a very few number of them, then yeah, you might spend your whole day taking samples from your device to do this kind of thing. So speed helps a lot there, and this is a big advantage of superconducting devices. So there are kind of pros and cons.
Got it. So we're at time. Please, if you weren't able to get your question answered, let's keep the conversation going on Discord. We have amazing mentors there to answer any questions that might be left over. One last question for our panelists. The IBM quantum processors are named after birds. Do you guys have a favorite bird?
Mm.
Turkey.
That yeah. I really like this one bird called the American woodcock. They appear in New York City during the spring, and they're very funny looking birds, so that's why I really like those. I don't think we'll be releasing a quantum processor named after it though.
Yeah,
Awesome.
that's a fun question. I wouldn't necessarily say I'm a big, an Amit bird fan, but I like flamingos.
Great. Last but not least, Ali.
Um, Turkey for me.
Awesome. Well, thank you guys so much for being here. It's not often you get to have the top minds in quantum hardware in one panel call, so we really appreciate you taking the time to answer the questions today.
Yeah, thanks everybody for joining. It was really great participating in this, and also thank you for organizing. Thanks everybody.
Awesome. Thank you
Thanks,
guys.
thanks a lot, everyone. Bye.
Mhm.